Cool. So what is happening? What is happening? I think what's happening is that I wanted to do some work on inverted indexes today. And what are inverted indexes? I'm gonna get to that. We're gonna get to that in a second. But, you know, there's just a lot of things going on today. A lot of projects happening in my head at the same time, too many. Inverted indexes, those are things I want to make better. Virtual table indexes, also something I want to make better. A lot of things I want to make better, guys. And not enough time. Not enough time to do them all. You know, I'm working on my radio status, you know. This is sort of what we do. We talk about things, we blab, 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 kill a little bit of time. Close some windows on your computer, if that's what you're into. Yeah, you know, basic stuff like that. So, let's see. Let's get back to our desktop view here. Basically, this is the issue we want to take a look at today, okay? Inverted index updates. Delete and rewrite duplicate keys. What is that about? Well, let's have a look. So we're going to use our favorite tool that we've used many times on this stream. We're going to be using the tool called Auto Trace. Here's what we're going to do. First, we're on some branches. I don't know. Let's get rid of these branches. Let's go over to master. That's where we like to be. Yeah, all right, so we rebase. Basically, here's what I'm talking about, okay? So we're gonna make a little quick example. We're gonna create a table. We're gonna give it a JSON column. We're used to that. We're gonna make an inverted index on the JSON column. What this lets you do is it lets you index the contents of the JSON column. JSON is like a container. We're indexing the container. And check it out, all right? So if we go and insert some data into this table, let's say insert into A, values 1, and let's put some JSON, foobar, a simple foobar kind of thing. We insert into this table, like so. And you know, okay, let's actually trace what's happening here. So we can do our auto trace thing that we've been using a lot. Auto trace equals on, comma, KV. Sorry I'm late. Can I get the notes from a classmate? You got 2 other classmates in this stream right now, Max, so you better hope that some of those 2 other people are paying attention, because I'm sure not. Basically, I'm going through the notes right now, though. This is about the notes. This is about the notes. So here's what's gonna happen. We're gonna insert a new value into this table, keyed at 2, and we're gonna watch the keys that it generates. Okay, so here's what we're doing. We're setting the primary key here. This is this line. And then this inverted index has 1 key right now because there's just 1 entry into it, foobar. So here we're inserting it. It's inverted index, it's magic. This is the key that we're inserting. Now here's the problem though. Let's say I said update A, set J equals, then I'm gonna change it to add a new key, foo. So I'm gonna keep foobar, right? But I'm gonna also have some new key, Baz Quooks. Okay, so here's the problem. Oh, and let's do a where A equals 2. So we're updating this row that we inserted and we're changing it so that it's got this extra key here. But here's the problem. The database is gonna do some dumb stuff. It's gonna delete all of the keys from the old entry and insert all of the keys from the new entry, even though the key from the old entry is the same as the key in the new. I mean, right, the key from the old row is the same as the key in the new row. So it's inefficient, you know? Waste of time. We don't like wastes of time in databases. We wanna make it less waste of time. So those are the cliff notes. Those are the cliff notes. Does it make sense? Here, I'm gonna make a little drawing while this is going on because I think the drawings are pretty fun. Where is that drawing thing? What is it called? It's called the heck is that thing called? Milton. Milton. I love this app. So let's see. What do we want to do? We want to draw. First, we want to get a good color. Nice yellow. We're going to draw like, what was our key? Our key was 2. So let's see. Our table is actually A is the ID. And J is the JSON, like this. Okay, so here's our 2. And our value was, oh gosh, this is impossible. Okay, it's okay. We'll just do foo points to bar. Yes. Okay, so then in our inverted index though, okay, so let's see. In our inverted index, which we will make red perhaps. Actually, yeah, let's put a little black divider here. Bam. Inverted index. It's got an entry from foo bar to 2. All right. So that's the thing. That's the key. Now let's say we update. That's what we did, our example. And the reason I'm drawing this is just so I can refer to it later. It's going to be so useful. So useful. Brush mode. So this is sort of state 1. Now here's state 2. State 2, we've got A, we've got J, we've got 2. Ooh, let's turn off these notifications, shall we? That seems like a good idea. All right. Yes, we've got this going on. We've got foo to bar again, foo to bar. But we've also got baz to quooks. And the problem is that we don't want this change to have to delete this key and then re-add it. That's just a disaster. You know, it'd be really nice if you could copy and paste in this app, but I don't think you can. I don't think you can. It's problematic for me. But that's okay. Anyway, so the point is that, yeah, when you are going to write this new key, so you're going to be writing foo bar 2. You're also going to be writing this other key, baz quooks 2. But you know, you don't want to have to delete this guy and rewrite it. That's just criminal. Criminal. This guy, we're currently adding it first and then removing it. You can totally understand what I mean with this crude drawing, can't you? I know I can. I understand what I'm talking about. But it should be pretty easy to fix. So we're gonna fix it together. It's gonna be super great. It's gonna be super great. Yay. Followed. Things were followed. So here's what's happening, okay? Somebody somewhere is encoding these keys. Who could it be? It's this thing, encode inverted index table keys. We've talked about this several times on this stream, I believe. And the person that is encoding this that matters, I happen to know, is somewhere around here. We have to keep following the chain up a bit. Index encoding. Encode secondary index, that's what it's all about. Encode secondary index encodes key values for a secondary index, right? So this is, we're gonna call this when we're writing things, and we're also calling this when we're deleting things. We're calling this like several times, and we have to find the right one and just change the way that we're behaving, I guess. So I think in this case, probably we just want to do it for updates. I think that's all it comes down to. row updater. I think the truth is that this row updater might be used by several people as well, which could complicate things, but maybe not too much. Let's see. I'm gonna turn this music down for a quick second because it's too loud in my headphones. I think it might be okay for you guys, but for me it's too loud. Turn down here. Turn up here. Now I think it's gonna be more balanced for everybody. All right, okay. So update row. Update row. We do a few things. We encode the primary index. We're not gonna touch that. And we basically just need to find the spot where, I think it's kind of around here, right? This is saying, for the old values, give me all of the things. For the new values, give me all of the things. And we sort of just want to deduplicate these things. And if there's any matches, if there's any things that are identical in new index entries and old index entries, we can just remove it from both of them, I think, is sort of what it's about, right? I think, yeah, I mean, that should be fine. All right, do you think, let's see, I wonder if these are actually even, these are sorted. That would be cool, but I don't think they are. I don't think they necessarily are. Let's see, when would this return more than one thing? For forward indexes, the returned list of index entries is in family sorted order. Well, we're not talking about forward indexes. Dumb question, is there a way for me to zoom in on the code on Twitch? No. Is it too small? I mean, I've been wondering about this. Like, I thought this was a decent size, but you know, I could just jack it up. There's no reason to keep it so small. Just jack it up. We'll just jack it right up. Size 12? What about size 14? How about that? Did that even change anything? Oh, current editor font, Fira code 12, defined in the color scheme. Okay. The color scheme font. Just a little menu diving, you know? Just a little menu diving. My fault for not having my glasses on me. Yeah, you know, I would say that is your fault. That is just horrible of you. Boom. We going big. We going big. Separate Twitch stream that's just going through IntelliJ settings. Yeah, I agree that that would be a pretty fun stream. All right, so now the text is bigger. I feel like I have to sit back a bit as well. It's pretty big. Pretty big indeed. So what was I doing here? Right, I was trying to decide whether I thought that the result of this thing is going to be returned in sorted order. And the answer is that I don't know. The answer is that I don't know. Let's see. Well, we have a special case for these inverted indexes, right? So let's see what this thing does. Encode inverted index keys, creates a list of inverted index keys by blah, blah, blah. All right. Kidobes, what is up? Thank you for joining. I want to figure out whether these things are sorted. It kind of seems like, I mean, this thing is saying each output key is prefixed by in key and is guaranteed to be lexicographically sortable. But that's not the same as that it's guaranteed to be lexicographically sorted. So I still don't know. Let's keep. Oh boy, you just have to go all the way down. All right. I think the answer is that it's not going to be sorted. That's just the honest truth, right? Because why? Like, I think this thing is basically deduplicate the entries since arrays can have duplicates. I think, okay, so the output of this thing is sorted. So I guess we can say at this point, encode inverted index keys on arrays returns a sorted slice of keys. So the question is, Does anybody else return a sorted slice of keys, or is it just this thing? That is the magic thing that we need to find out. The magic thing. I think you guys could hear that, so I'm going to turn it off too. So let's look at the case for objects. JSON objects. JSON objects are not going to be sorted by default. So if we don't do any sorting here, we're definitely not going to have any sorted output keys. So I think in this case that, yeah, doesn't look particularly sorted to me. So I think we'll have to do our own sorting higher up, and that's fine. That is fine. It does not bother me too much. So let's go back to where we were. Where we were was in the part where we're actually updating rows in the database. Updater? Right. So in this case, I think basically what we want to do here is have a special case for inverted index entries. Although, you know, maybe this is something that we could apply to everybody. I don't know. Like, what happens if you update and nothing changes? Do we actually rewrite secondary index entries for non-inverted indexes? That would be kind of a cool thing to fix at the same time. So let's find out. Create table T, A int primary key, B int, C int, index on C. So if I say insert into T values 1, 2, 3. Let's make this bigger too. The viewing pleasure. So here we're inserting the key into the primary index like we were before, and we're inserting the key into the secondary index. So the question is, what happens if we update, let's see. Let's turn this off for a sec. Let's look at our table definition again, show create T. So our index is on C, and the question is, if we update this table such that this index doesn't change, do we write anything? So I think that in this case, that would be editing the table to change B, but no other columns change. So I guess I say, first turn my auto trace back on, then I say update T set B equals 10, where A equals 1. Was it 1 that I inserted? Yeah, 1. So this I would expect to only write a change to the primary key and not change the index at all. What does it do? It weirdly did a lot here. And I think that was, I don't know why I did that. Let's try that. Let's just try that again to make it a little bit less noisy for us. It always does a lot. It's a bit mysterious. Maybe updates are just kind of noisy in this tracing view. Oh, I see. It's because I set the auto trace to not have the KV filter. Let's try this again. One more time. That's a nice, pretty output. And in this case, it looks like we only do update the primary key, which is great. But I think the reason that this is happening is actually a different layer than the one that we're touching. So whatever. Okay, so that was a bit of a tangent, but I think the point is that what I was trying to get at is that I don't think we actually have to do any work here unless we're changing a secondary or an inverted index. So we can add a little conditional for that. We'll say if deduplicate the keys we are adding and removing if we're updating a uninverted index. Inverted index. For example, if we have imagine a table with an inverted index on J. We'll just construct an example so we don't have to rethink of this every time we come back to the code. We'll just use the same example we did before. So we'll say if we update the JSON value to be foo bar, comma, baz, quotes, we don't want to delete the key for re-add it. That would be wasted work. So we are going to remove keys from both the new and old index entry array if they're identical. Cool. Okay, so let's see. How are we going to do that now? We'll say if ru.helper.indexes of I dot, wait, do we not have enough? Oh, that's index entries. We want indexes. So if this thing is inverted, do we not have that information? We should. Oh, type. If the type is index descriptor inverted, let's just paste this big block comment inside of this block. Maybe that'll be nicer. It's always a question. Do you want to put your big block comment about a conditional inside a conditional or outside of the conditional? I always go back and forth. I'm probably not consistent about it. So, right. We want to, I mean, I basically think that we should sort these and merge them together rather than hash them. Well, I don't know. Do you want to hash them or would you want to sort them? I think the hashing might be kind of expensive. Because, I mean, for example, if you had a giant megabyte payload, well, maybe it's kind of about the same. I don't know. I think one advantage of sorting and merging is that you can do it in place. You don't have to allocate any new memory. So I kind of think that we should just do it that way. Avoid those allocations. Because I think this is a pretty hot path. You don't really want to allocate too much when you're doing stuff like this, if you can help it. Okay, so yeah, sure. We'll sort these babies. What is inside of these index entries anyway? They have a key and a value. So I guess we kind of need to, sort on both, I guess. We need to sort on both. We can ignore this. Yeah. Okay. So we have this snazzy go sort.slice method that we can use. We're going to sort and merge the lists together to get this behavior. So we're gonna do ru.new index entries using, I think you give it a less func, and I think we can reuse this func for both of them. So let's just define it inline for now, and then we can pull it out later. So the purpose of this less func is to tell you, I think the way it works is that this sort thing will apply sort of a fixed sorting algorithm, and when it needs to compare two elements, we'll call this less func. So pretty simple. So we have to figure out whether one thing is less than another, and we're gonna say, let's take the first entry. We can call it I entry. It's kind of ugly. We'll call it left and right. I don't know. So, and we're gonna say if left dot, wait, is this not a thing? New index entries of I. Oh yeah, sorry. This is actually not quite right. We want to be sorting. This is sort of tricky. New index entries is a slice of slices. And the ith slice of new index entries is the thing that we're looking at right now, and not, yeah. So we want to really be, these need to be like, I don't know, it could be K and J. Why don't we make, no, I think it's idiomatic to have it be I and J. So what we're going to do is we're going to define this thing as another variable. We'll just call it new index entries. Then we can stop referring to this RU thing. And then we can say if left dot, right. So first we're going to compare on the key because it comes first, and then we're going to compare on the value. So if left dot key, and I think this is a byte string. So we want to use, is there like a bytes dot less or something? Bytes dot compare, yeah. We sort of want to say if byte comp is equal to bytes dot compare left dot key comma right dot key. And we'll want to say it's less if, how does this work? I think comp is going to be negative if it's less, right? The result will be -1 if A is less than B. That's exactly what we want. So if comp is not equal to 0, return comp is equal to -1. This is true if it's less. All right, but if it is equal, then we have to fall back to comparing on the value. So we can just say return bytes.compare left.value right.value. Cool. This does not seem happy. Oh, right, because it has to be a Boolean. And it's less if this thing is less than 0. Let's be consistent. We'll do less than 0 here as well. Doesn't like this either. What is a roachqb.value? Ooh, right, it's a struct. We have to look at the raw bytes because the timestamps do not matter here. That is not important. Cool. Okay, so I think this is right. And then what we're gonna wanna do is do the same thing to the old index entries. But we don't want to rewrite this function. So let's actually just pull this out into its own little variable. And since it's also parameterized on the slice here, I think we need to pull it out into a function that returns a function somewhere else. Wait. So we'll call this compare index entries. Index entries comparison less func. How about less func? This is going to be called index entries. Then we return this function that we can use as a comparator. All right, so I'll put a comment on this guy. It says index entries less func returns a less function suitable for sort.slice that operates on the index entries passed in. This can be used to sort index entries. All right. So we're gonna do two things. We're gonna sort we can actually inline this thing now. That's nice. Well, no, we won't inline it because we're using it twice. We're going to sort both our new index entries and our old index entries. And then we're going to merge them together, removing duplicates. Isn't that fun? That's a fun little mergey guy. So how's it gonna work? Are we gonna just re-implement a little mergey guy from scratch right here, right now? That sounds fun. I think that's the way to do it. We sort of want to define an equality function as well, to be honest, because I guess we could just save these things and reuse them in our little mergey thing as well. But not quite, because this is going to return a Boolean, is it less? And what we really want is a a Boolean, is it equal? That's annoying. That's very annoying. We might just have to define two functions. That's okay. We can actually define it on this struct directly. So we'll make a, no, I guess we also need an equality, don't we? We sort of need both. I forget. I don't know. Let's just start writing it and we'll see what we'll see what happens. So we're gonna, how does this work? We're gonna keep a pointer in both. We're gonna advance a pointer if one is less than the other, something like that. And if we see an equality, we're going to, what are we gonna do? Do we shift the next one down an element or something like that? To avoid extra space in our slice? I think that would probably work, but I need to think about it. We can try. Right. All right, so we're gonna call, the problem is we already have an I here, so we don't wanna really call this thing I. We can call it L and R again. It's not how, can you not do this? So what's our condition? Our condition is basically for L is less than len new index entries, and R is less than len old index entries. So while these things are true, we're gonna keep working. And I think it's a little tricky because we're gonna be editing the length of this array if we're removing duplicates. This thing is gonna need unit tests for sure. So it probably needs to be its own function, and I'll do that eventually. So we're gonna say merge the lists together, removing any, no, well, we're not merging the lists together. Sorry, we're just remove duplicates, remove entries that are duplicated across both entry lists. That's what we're doing. Okay, so, well, the obvious thing to check first is the thing equal? Is the thing equal? So we'll say, and this is where we need that comparison function. You know, I think it would be good to just have a variant of this thing that instead of returning true or false, it just returns that comp value. You know, -1 if it's less, 0 if it's equal, and 1 otherwise. And I feel like it's annoying that you can't just have something that does both here, but just because Go is sort of irritating like that, we sort of have to, I think. Well, maybe, here's what we'll do. Maybe we'll change this thing to be a comparison func, and then we'll just, we'll turn this thing into a less func on the fly when we're doing our original sorting. So we'll just return comp here, and then otherwise we'll just return, yeah, like so. Change our comment a little bit. This returns, this is going to return an int as well. This returns -1. Let's see, it will say the returned function returns -1 if the element at I is less than the element 0 if they're equal, and 1 otherwise. Right. So then we have to modify this thing a little bit, irritatingly. We have to go like this. It's so gross, honestly. New index entries comp. Then we'll say return new index entries comp of I, comma j is less than 0. That's what we'll do. That's the way to be slightly reusable. Old index entries comp. Let's copy this. All right. Okay. That took longer than I wanted it to, but that's fine. We're making progress. All right, so now over here, what we can do is we can just use our comp functions directly, I think. Sort of. I think we need to extract this thing into a function. Oh, this is just so annoying. This is just so gross. What we need to do is make a new function just to compare these two things specifically. So we'll call it func compare index entries, and it'll take actual concrete index entries this time. So I, j, SQL base dot index entry. And this is where we're going to stick this logic here. Yeah, instead of I and j, why don't we call it left and right, just to keep things consistent. It's going to return an int. And over here, we can just return compare index entries I, index entries j. At this point, I feel like we could actually even just get rid of this, but whatever. Enough futzing. So now over here, what we can do is we'll compare these things and then make a decision. So we'll say comp is equal to new index entries, compare index entries, new index entries of I, new index entries of j. Or wait, we want L and R. Okay, so here's the thing. Now we finally have the opportunity to do something. We'll say if comp is 0, this means current elements on the left, the elements are identical. We want to remove them from the list. And so what that's going to mean is that we're going to want to teach this loop to sort of move the next element backwards by a slot, in a sense. So it's sort of like every time we advance L and R, we're going to want to move the element at the current actual index back to the L and R, the sort of logical L and R. So we sort of have an input L and an output L and an input R and an output R. So how's that going to work? I think what we're going to want to do is advance. On every step, we're gonna be advancing the physical element, no matter what. But we'll only advance the logical element if we didn't have an equality match or something like this. I don't know. It's a little bit gross. A little bit gross, to be honest.
If for no other reason than we do not know what it is. We do not know.
Let's actually start with let's start with the other cases, because I think it'll make it more clear. So we'll say if comp is less than 0, advance the left element. So we can say L++ and continue. Compare the next two. Guess we can do a switch. Okay, so and then I think that this is sort of where we're wanting to do something different. So let's look at an example. Say we had 0, 3, 5, and we had 1, 2, 3, 6. In this case, what we want to do is once L is equal to 1 and R is equal to 2, we want to, every time that we go forward, so every time, let's see, so essentially when L becomes 2, when L is at this slot, we want to be moving the current element of L to the last logical, so the output index, which is going to be at 1. So we sort of need an L in and an L out. I think. So while the L in and the R in are less, we're going to do our work. And at every step, we're going to want to say that L in, so new, let's also rename these to new and old just to keep things really clear. New in. Say the left is the old actually, so we'll say old in, old out. New in, new out. Okay. New in, old in. This has to be old as well. All right. This is a bit tricky. Every step of the way, basically what we want to do is advance. So we'll say first we're going to advance our old in since we're at -1. Let's keep things correct here. We're going to advance old in and then we're going to set old index entries of old in is equal to, no, old out. This is confusing. Old index entries of old in. I think this is basically what we want. And also, yeah, in this case, we want to advance both of them. So old out plus plus. And likewise for this one, this is basically the same. New in, new out, new index entries. All right. How much sense does this make? None. If we're at 0 though, what we're gonna do is we're gonna say, we're gonna increment the input, but we're not gonna increment the output. So we'll say old in plus plus, old new in plus plus. So we increment our input indices without touching our output indices. Next time through the loop, we'll shift the next element back to the class output index, which is now lagging behind the input index. This is so dumb. I mean, honestly, like there should be some code that does this in a generic way already. Okay, and here's the other thing though, is that we actually can't just give up if either of them are out of bounds. We have to go until both of them are out of bounds. So we have to change this condition as well. So we'll just make it a regular for, how about, and we'll have just conditions at the top. So we'll say if new in is less, if new in is greater than or equal to new index entries, len. Let's say if they're both, and old in is greater than or equal to len old index entries, then we're really, really done. We can break. Otherwise, if new in is greater than or equal to len new index entries on its own, then we want to just advance until the end for the old side. So we'll say, we'll basically copy this part here and leave. Otherwise, if old in is greater than or equal to len old index entries, then we'll copy this part. It's really, I think it would be cool to make this a little generic thing, generic-ish, with a, takes a comparison function. Because I think that this is just heinous right now to have to repeat this if I ever do it again. We could start doing it now. Why not? So let's go to some utility package. What would that be called? Search and shuffle. What about, what would this be called? Merge? Or deduplicate cross two lists? That's such a weird name of a thing. What are these? What are these things? Just some, oh, it's a binary searcher. What's this? It's a shuffler. This is suspicious though. Yeah, I mean, I guess, I thought I also made some kind of distinct machine recently. Didn't I do that? Where would that live? because I want to follow that same pattern. I think I did it inside of this index encoding guy. Inside of JSON. Uniquify byte slices. Util unique. Okay. Yeah, so what we'll want to do is just we'll make a util dot list dedupe. Just make a dedupe. But it's not just dedupe because that's the same as uniquify. I guess maybe we could just stick it into this package. So we'll make it called unique dot list unique or something. Distinctify, uniquify byte slices. Uniquify I just don't know what a good word for this would be. What could a word for this be? Can't think of a word for it. I don't know, whatever. We'll just go with, uniquify cross slices. And it'll take a left, this will be anything, and a right, anything. Uniquify across slices removes duplicates, things that are duplicated across both of the slices from both of the slices. It assumes that both slices are already free of duplicates themselves, duplicates internally. It returns the slices which will have been sorted as a side effect. Okay, and this thing is also going to take a comparison function that will compare two of these interfaces. LR interface and it'll return an int. And this whole thing will return interface, comma, interface. Okay. So then we can go and copy that stuff we were writing over here. So we'll start calling these left and right, I guess. And for this, we'll have to make a new thing that will say return comp left of I, comma, left of j less than 0. Same over here. Okay, so first we sort our slices. Then we are going to rename all of these things left and right as well. Go back to LNR. All right, that was a lot of manual stuff, but I think we're basically done with that part now. So basically, let's see. If we're done with both, then we can completely quit. If R is the only one that's done, we advance L, we set L, well, this is gonna fail, isn't it? Because if L in is sort of an off by one problem. Cool. Ruffy, join the one person party. What's up? We're writing generic code in Go, something that we never do. Do you think that there's, okay, look. Do you think that there's a function that takes two lists, sorts them, and then removes things that are in both sides? I don't think there's such a thing. I don't even know what you would call such a thing. Currently, I've called it uniquify across slices, but I think that that's a horrible name. And I don't know what else you could call it, really. It's like by unique or something. Maybe the Haskell people could tell me. Maybe there's a lens for this. But yeah, I mean, it's a little bit annoying, honestly. And I think that I'm failing to be good at this. Because the reason that I'm failing is actually that I'm trying to do it in a very overly efficientized way where we don't do any extra allocations. Lodash.com/doc/difference. Creates an array of array values not included in the other given arrays. Not included in the other given arrays. Okay, so this is sort of like difference. Yeah, it's related. It's certainly related. Yeah, these like JavaScript libraries are full of weird little like functional list slicing machines. Chunk. Difference with. It's sort of like difference with. Difference with? No, I don't know. Difference. Let's go back to looking at difference. difference. In this case, it returns 1. So it's sort of like difference, except it has to work on both sides. So in this case, I really would want a list that had 1 and 3 in it. No, wait. What I would want is 2 lists. One that had 1 in it, and one that had 3 in it. Call difference twice with param orders reversed. Yeah, I think that's accurate. That's accurate. Difference. Inefficient. Yes, it's far too inefficient. You have to be the most possible efficient. And that, for some reason, in my head involves a complicated merge loop. That is definitely going to be incorrect. Because you don't want to make a new array, you know? You want to just edit that old array. Basically, my idea is that we have 2 indices for each list, an input index and an output index. And if we are going to advance one side, we can bump both the input and the output indexes. But if we see an equality, then what we want to do is bump just the input index and then keep the output index at the same. And then furthermore, in every iteration, we set the current output index to the current input index, so that we're sort of like over time shifting backwards. I think that it makes sense, at least in my head, but it's a bit tricky because you have these edge conditions. Yeah, the other thing is at the end, I think what you need to do is set the length so that you don't end up with any weird stuff. So you'd say like left equals left up to left out, and then same for right. Okay. So I think the fundamental problem though is that when I get to the end, let's say we're in this case. So this case says that we finished the right side and we haven't finished the left side. In this case, we want to bump both of them. Oh, you know what it is? I think we just want to switch the order of this. We just want to set this first, and then we want to bump both of them. And then we're going to continue. Then we're going to come back here, and if it's over, then we quit at this point. So I think that's going to be great. Just want to do that ahead of time. So then what we do after this little end condition loop is that we come back, we do our comparison on our input side. If it's less, then yeah, this is the mistake I made. I just have to do this first. When you advance one of the sides, you set it first. You sort of shift first, and then you advance afterwards. And if it's equal, we advance the input sides on both and continue on in our lives. I think this is going to be great. Okay, so let's write some tests for it, shall we? Turn left, comma, right. Let us write some tests. Let us write, where is the thing that lets me generate a test case? Where is that damn thing? Give me generate, command N, tests for function. Okay. Okay. So our test cases are going to be slices of integers. We're going to get rid of most of this stuff here. We're just going to get rid of all this crap. I think these generated structs are always a little bit overwrought. So we'll say expected. Oh my God, is this a Twitch spam thing? How do I banned? Have you ever banned somebody? That was sweet. All right, so we have left, right, expected left, and expected right. And these are all going to be integers. So the test cases, let's see. The first one, we're going to have left as 0. We'll do like sort of a basic case. Ooh, and also this thing is expected to have sorted things. Well, let's just start with sorted things and we can test that other part of it later. So we'll do 0, 5, 7, 10. Uniqueify versus uniqueify. Isn't this something? What about Quibi versus Kibi? What's up with that Quibi? It's everybody's spamming about it, and I'm offended. It's just offensive. All right, so on our right side, we're gonna do 1, 5, 7, 11. Why is this not? Oh. Why is this unhappy? Why? Do I need to say it's an int? You still haven't figured out what the... Yeah, man. I don't know what that thing is either. I haven't bothered to click on it ever, but man, it's just everywhere. Everyone's like got ads for it and stuff, and it's super gross. Okay, so for our test case, we're going to say actual left, actual right is equal to uniqueify cross slices left comma right. Wait, we'll say tt.left, tt.right. And then we'll say if ints dot, what's wrong with this? Oh, it needs a comparison function. That's right. Func lr int return left less than right. Ooh, but this needs to be an interface. I mean, need to cast. That's super gross. Super gross. It's still unhappy. Why? Oh, because it's got to be a slice of interface. Oh my gosh, this is so nasty. So nasty. Do I have to go like this? Does this even work? It hurts me. The comp closure also needs a return type bool. It needs an int, but you are right. Thank you, Paul. What's up? I just don't know about this crap with the interface stuff. It's so yucky. This is why maybe I shouldn't have even bothered to try to make this code generic, you know, because it's impossible to do it nicely in Go, but that's fine. All right, so then expected left, expected right. So the left we expect to have 0 and 10, and the right we expect to have 1 and 11. Great. This is unhappy for some reason. Cannot use type bool as type int. That's because, doesn't int have like a comp function already? Int? Maybe not. If L is less than R int, return -1. Else if L dot int equals R dot int, return 0, return 1. Okay, so then we get to say if actual left, maybe isn't there like a deep reflect dot equals, deep equals? If it's not equal, actual left, left, expected left, tt dot expected left, then t dot error f. Expected this, got this. Actual left. Wait. Expected left, actual left. Okay, and then we can do the same thing in the opposite direction just to prevent us from having to do too many test cases. But we'll do that in a second. Actual right, expected right, right, right. Okay. Yeah, so we sort of want to put this in a little loop. We'll say for I in oh, I know. We can just say for I in range test. We'll just add all the tests up again in the other direction. I'm always wanting to, like, for some reason this problem just has me editing lists while iterating over lists in like 5 different places. What happens if you append to a thing in the middle of it? Okay, arig tests is equal to tests. Arig tests. Test equals append. Test. I have to name this struct too. Type test case. Uniquify across slices test case. UAS test case. Simple. Okay. UAS test case. How about this? What's wrong with this? Oh. Okay, all right. We're getting there. So then we go and append our tests backwards to the new end of the test list. Test equals append test, UAS test case, and we'll say left is equal to test dot right. Left is equal to right is equal to test dot left. Expected left is equal to test dot expected right. Expected right is equal to test dot expected left. Bam. Okay. All right. That is a test, I think. Let us run it. It claims to have passed. Wow, it's so fast to run tests when you don't have like 20 million packages to compile, is all I'll have to say about that. Did that really work though? I'm kind of suspicious. It does not appear to have worked. Oh, it's because I didn't put a not. Okay, so I was testing that my tests were all failing, and they all successfully failed. All right, sweet. Sweet. So the current status is that it didn't work at all. So that's cool. Let's figure out what's going on, shall we? Okay. So we sort our inputs. Our inputs are successfully sorted. Go up into this loop. None of these things are true. We compare the first two inputs. We should get -1 because 0 is less than 1. Except we get 1. Is that expected? Oh, it's because I have this. I think I have this backwards. I think I have it backwards. Right? If right is less than left, then I want to be advancing right. Yeah, so I think I just have to switch these. Okay, no problem. Try again. In we go. Do. All right, so we're advancing left. So L out and L in should be 0 both, correct? We advance them both. We get out of here. Now we have now the other one should be greater, so we should advance the right side. Good. Now they should be equal, and this is where we should do something. Yes, they are equal. We advance the inputs. Maybe this is just gonna work now, I don't know. Continue. Continue. Fail. So it's a little different now, that's good. So in the first case, I think it was good. We wanted to see 0, 10, and we got, in 111, we got 0, 10, and 111. But in the second case where we have everything flopped, it didn't work. Expected 111, got 111, 11. Now this sort of seems to me like we just didn't edit the length properly because we just have a duplicate at the end. So let's go back and look at what we're doing. I'm guessing that we just need to subtract 1 from this, and the reason for that would be that once we run off of the end, once we run off from the end, I don't think we have to subtract 1 because then these would be wrong too. Why don't we stick a breakpoint there, see what's up, rather than have to brain it out. So right now, what do we have? We've got 111, 11, 11. Do you think let me just check something real quick. What happens if I just duplicate this and then do it? Did I screw up the like flopping code? Did I screw up the flopping code? I did screw up the flopping code. Well, that's good. But how? Oh, it's because they get edited. Oh, that's so annoying. I need to copy this. I need to deep copy these things. Oh. Isn't there some sort of, is there a reflect.deep copy? Is there some sort of deep copy thing that we have? Deep copy string. Just random. deep copy Golang. There's a, oh, it's in some random package. Get lantern? What even is that? Well, I guess in the test cases case, I know that it's just an interface that has ints inside, so I guess I could just sort of do it by hand. For each test case, add a flipped test case. Write copy is equal to make interface len test.write. Left copy. Left. For I in range, write copy. Write copy of I is equal to test.write. Vice versa. Okay, I think this should fix the problem. Left is going to be write copy, and right is going to be left copy. Okay, now we can go back to writing some tests. Okay, so for this, we're gonna have one of, let's see, maybe an empty one. Expected left will be 0, 5, 7, 10. Expected right will be empty. Maybe both will be empty. We'll do different lengths, I guess, with all different elements. 3, 5, 7, and then like yeah, maybe this one. So this should be 3, 5, empty. Different lengths, all completely different. 3, 5, 7, 8, maybe all the same. Okay, let's run these bad boys. Something failed. Interface is something. I think it's just a problem with my test framework again. Interface blah is slice of interface blah, not int. Okay. Oh, I just forgot to do anything smart here. All right. Yay. All right. I believe that it works. I believe that it works. So now we can go back to the problem at hand. That is exciting. Very exciting. Back to the problem at hand. Get rid of all this stuff. Goodbye. We've got new index entries. We've got old index entries. What's going on? We don't even need this anymore. All we need is one function call to unique across slices old index entries, new index entries. And we'll just set them old index entries, comma, new index entries equals. And this needs a comp function. We can actually just get rid of this whole thing and keep just compare index entries, which is better anyway. Compare index entries. No? Oh, they need to be slices of interface. How does sort.slice work again? What is the signature of sort.slice? Takes, oh, it uses, oh man. Okay, I guess we should just do that too then, huh? Guess we should do that too. Man, this is whack. Go is just whack. Okay. How does it work? Reflect value of slice. What the heck is this stuff? Is this only fast because they did it fast inside of Go? Oh man. Left slice is equal to reflect dot value of left. Then how do I get how do I turn this into a slice? That's my question. Left slice dot slice? No, that gives me a thing at a spot. Is there no way to just like get this into a slice of interface? Let's go back to what they're doing here. Quick sort func. How does it work? How does it work? Where's the part where we actually in data.less? I guess this is why we pass in a function that actually takes that actually knows the context of the slice that it's looking at. This is so bad. Because how are we going to possibly do this? Like, we're literally manipulating the slice right here. So I don't really see a way around this. Unless I can just say, I mean, I guess I could say like, all of these things could be reflect operations. So you could say like left dot, or left slice dot index, or set slice, no. How does this work? There's like set at. I thought there was something for this. Set at. Oh, maybe if you just say slice, it'll give you the thing and then you can set the thing at the slice. I don't know. This is very demoralizing. Because realistically, if we wanted to make this work, we'd either have to figure out this crazy problem or make this just not generic at all. Like, what would we need? We would need a function that sets a value in the slice at element X to the value at the slice at element Y. We would need a comparison. And then we need to be able to set the length, which I think you can actually do, right? You could say I don't know, maybe I give up about the generic. Maybe I should just give up about the generic. No, maybe it's actually not that bad. Maybe we can still do it, because maybe instead of returning things, what we do is we just edit it in place. Does that work? No, because this, I don't think you're allowed to edit the length of a slice in place because you don't have, I mean, you could pass in a pointer to the slice. But then you have something that's really gross. Maybe that's what we do though. I don't know. Like, where does this thing do validation? Where does this validate? Oh, it just panics if it's not a slice. All right. Well, let's maybe assume that this thing left and right have to be pointers to slices. And we're going to pass in a comparison func that takes two integers. And it also, let's just add some more requirements here. The slices also have to be sorted ahead of time, or else this won't work. Comparison func compares the elf index of left to the rth index of right. And then we also have to say left set, or this is so gross, left set at index, left set sets the ith index of left to the jth index of left. Right set sets the ith index of right to the jth index of right. Have you ever seen something so nasty? Left set. Right set. I, J, J. Okay. So we get rid of this stuff. We can move these up to the updater. Sort.slice. Old index entries. Return compare index entries. Old index entries. Old index entries. Same here, except this is new. All right. Then what we need to do is pass in a function that compares across the lists. So this is going to be func l r int return old index entries of L, compare index entries, old index entries L, new index entries of R.
This is what's been taken from us. This is why the new music and dance culture
No?
is so important. This is why drug culture is so important.
Then I'll say func ij int. This is going to say old index entries of I equals old index entries of J. And then likewise for this guy, new okay. Too many arguments. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just need to get rid of this guy. Okay. This is problematic. Why? Oh, because I set the argument of this thing wrong. No, that seems right. Comparison func. I think this needs to be a less func again. Less func. Wait, no, it has to be a comparison func. What's wrong with this? Oh, yeah, I see. It needs an int. Okay. Okay. So that's doing something now. Now we just have to figure out this reflection business. So we'll say left slice is equal to reflect dot. And I think there's a way to, this is like some pointer business, right? What does this do? No. Value of? What does this do? It turns a new value, initializes to the concrete value stored into the in the interface I. So in this case, this is going to be a pointer to a slice. Left slice pointer. Right slice pointer. Now how do I dereference something in reflection land? Left slice pointer dot. How does one do that? Pointer? No. Don't know how you're supposed to do this. Because I think if I just said left slice, well, why don't we just try it and we can see what breaks. Now over here, what we want to do is say, we want to get the length. So we want to say left len is equal to left slice pointer dot len. I think this is just going to fail right out because I think it has to be this is going to be a pointer, but that's fine. Right len. Right len. Left len. Right len. And then here we get to call our special function. This is so goofy. So we get to say left set and then L out, R out. No, L out, L in. This is also so pointless because like who's ever going to use this code again? Really, it's making me think that I shouldn't have bothered making it generic after all. Right set. R out, R in. Now here, our comp func is going to be, we're just going to get to call comp func L in, R in, L in, R in. I mean, that's kind of nice. It's kind of nice. Grab this. Grab this. And then over here, we can say left slice pointer dot set len L out. Is that right? Or is it L out minus 1? Wait, or is it L? No, I think it's just L out, right? If I had foo of 1, this is gonna be a 1 length slice. Then same for right slice pointer. Okay, we return nothing. We return nothing. We've edited the slices. This is some janky stuff, really janky stuff. So then over here, we're gonna actually pass in the index. I mean the pointer thing. Wow, no way this is gonna work. Let us look at our tests and fix them now. So now it has to pass in the pointer, but luckily we can go back to using these as ints, so that's nice. So we'll say replace interface with int. Why is that happening? How about we just replace interface with int? There we go. And likewise here. Cool. Then here, I think we want these to be ints as well. Int. Now we just get to edit the call to our actual function again. It's going to be a bit different. So this is going to say return tt.left of L is less than tt.right of R. Much simpler. And then we want 2 more functions. One is going to set stuff in left. So we'll say tt.left of I is equal to tt.left of J. And this one likewise for right. These don't return anything. Oh yeah, we actually wanted to keep that comp func thing. If this thing return -1, also if tt.left L equal to tt.right of R, then return 0, otherwise you return 1. Okay, okay. Now we can run our tests again and watch them explode. Right, we just run now. And we've mutated them, that's fine. So we'll just say tt.left. We want tt.left to now equal tt.expected left. Try again. Whoop, one more thing. tt.left, tt.right. Wrong type. Can I not just, I guess I have to make these V's. Okay, so now at least we have what I thought was gonna happen. Call of reflect.valueLen on pointer value. Right. So what we want to do here is dereference our pointer somehow. Do we even have to pass in the point? I don't know how reflect works at all. Maybe if you pass something into reflect, you actually have, no, because it will get copied. So that's not gonna work. We do have to look at the pointer and dereference it. But how? How? Ooh, indirect returns the value that V points to. If V is a nil pointer, I think we want this indirect business. It's kind of a funny way to describe something. So we'll just say left slice, rename these, and then we'll just stick a call to indirect on the end. Indirect. No? Wait, where was that? I thought I had something that was called, oh, it's just, I see, it's a function, not a method. Indirect, like so. All right, now what will happen? Reflect.flag.must be assignable using unaddressable value. Well, I have no clue what that means. Must be assignable. What the heck does that mean? It panics if v's kind is not slice. I think v's kind is slice. What is this must be assignable? Panics if f records that the value is not assignable, which is to say that either it was obtained using an unexported field, or is it's not addressable? Not addressable? Does anybody else call this in the world that I can pretend to copy? In this case, v see, why wouldn't this be so-called addressable? Don't know what that means. Maybe when we where was that? What? Who's calling this? Oh, reflect dot value of. If it's not a pointer. Yes, indirect. What is this? What is this going to do? Maybe, I wonder if maybe this setlen has to happen on the pointer type. That's just a guess. It's just a guess. Left slice pointer. Yeah, you know, that's probably what it is, because how could this happen on the value? Right slice pointer. That's probably what it is. Let's hope that's what it is. No. Unaddressable value business again. I just don't know what that exactly means. Unaddressable value. What is that about? I'm gonna Google it. Unaddressable value Golang reflect. reflect.new. What does that even mean? Do I just have to? We can try it. We can certainly try it. Reflect.new. What does it mean? New returns a value representing a pointer to a new 0 value for the specified type. Okay, but then how do we set it? Reflect.new. What? Just clicking on random things until I find something that looks like it might help me. Must be assignable. Don't really get this. I just don't understand like what unaddressable. What does it mean to have an addressable versus an unaddressable value at all? Ooh, there's a laws of reflection. Maybe this will help. Reflection goes from interface value to reflection object. This looks relevant. To modify a reflection object, the value must be settable. This is a cryptic message. Settability is a bit like addressability, but it's stricter. It's the property that a reflection object can modify the actual storage that was used to create the reflection object. Settability is determined whether your reflection object holds the original item. When we say blah, we pass a copy of X to value of. Yeah, that makes sense because it's a copy. But I think that we were passing a pointer, so I don't understand yet. If we want to modify X by reflection, we must give the reflection library a pointer to the value we want to modify. But that's exactly what we're doing. It's already exactly what we're doing. We're giving the reflect library. This thing is a pointer. left is a pointer. So we're taking the value of the pointer, and then we want to be editing the thing. Or is it saying that we need to give this thing the address of that, and then we need to indirect it twice or something? That would be wacky. That would be super wacky. Ooh, the LM. So maybe this indirect business was not what we wanted. We want LM this entire time. Maybe that's what it is. Okay. Okay. So what if we just say LM? LM. I was just using indirect and not LM. LM returns a value that the interface V contains, or that the pointer V points to. Okay. I think maybe that's the problem. Let's just get rid of this pointer stuff. And instead of this indirect, we'll just say value of, and then we'll say LM to get the underlying array. And then way down here, maybe if we just say left slice.setLen, we'll feel happier. Could that be the problem? No. Call of reflect.value.lm on slice value. Okay. What's the problem with that? I'm not allowed to do it. It has to be an interface or a pointer. But it was, I thought. Unless we're not passing the pointer to it anymore in the test. That could be the problem. Aha! Only did it on one of them. All right, let's hope. Yay! Oh, that's good. That's great. Did it actually run all the tests? Why don't we make a little subtest thing? Strconv dot I2A I func t testing dot t. Okay, grab all this stuff, stick it in here, then we'll run again. Maybe see a bunch of, all right, cool. 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 Oh, this is good. All right, so now back in our actual thing, I think that we might be good to go. Let's compile. Let's compile it. Okay, should be almost done. Then we can see if we are deduplicating stuff. the way we expect. I think it should be possible. Not likely, but possible that that will work. That would be pretty cool. Okay, so we'll go back to our test. Create our table with our JSON. We'll insert into our table. Turn on our auto trace, then we'll update and see what happens. I'm guessing this is probably gonna like panic. Something like that. Wait, wrong update statement. Okay, it didn't panic, but it also didn't work. So really we were expecting to not see this and also not see this. That's fine. That's fine. We didn't expect it to really go so well the first time anyway, did we? So why don't we, wondering if the problem is that we didn't, Why don't we print out what we've got here as a way to start? About to update, about to change update keys. And then we'll put the old and we'll put the new. Then we'll do it again down here. Or we'll say changed update keys. I guess we should probably write a little logic test. That would be faster. We'll do that while this is compiling again. So we'll do this in the exec builder, and we'll do it inside of the, should be an inverted index test, right? Update. Probably some update tests already. Why don't we, yeah, I forgot we can do it with arrays too. That might be a little bit of a slightly simpler set of tests. So why don't we do it? We'll say, test for array inverted indexes. How about we go over here and we'll say update f set we'll edit this one maybe. E. So what is E? What's the name of the column here? It's B. Okay. So set B is equal to, and we'll add 1 to the expected output here. So right now we've got 0, 1, 7, and null. So we'll add 1. 0, 1, 7, and 10. I meant not null. Where is A is equal to 0. A is equal to 0. Query T KV trace. We'll see what that produces, but in the meantime we can do it by hand again. I mean, it seems good, honestly, because the left update keys, there's nothing in the delete, and there's just one thing in the new. So how come that's not working then? Seems like it's kind of should be working. Oh, it's because we copied the slice. Okay, that's it's very simple to fix. I think this should do it. Well, let's just, we'll actually do it. Just keep with this and we'll set it back at the end. So we'll say ru.new index entries of I equals new index entries. Likewise, the old ones. Make test op logic. Files equals inverted index. Okay, our tests ran. Well, this is great. This is exactly what we wanted. I think. We want to be only adding exec build. Zero, 1, 7, 10. Oh, okay. I guess in this case we didn't really want to emit anything. What if we did 15 as well? And then we'll do rewrite so we can actually check it. Test flags equals rewrite. Scan. Put init put 15. Oh, this is great. This is exactly what we want. So we'll do test that updating on a row that edits inverted index entries doesn't delete and re-put things that exist both in the old and in the new value. This case adds 15 and removes 1, so we should just see those commands. So it's deleting 1 and adding 15. Solid, 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 solid. Okay, let's make a commit for this stuff. Can get rid of those prints as well.
Yes, there is fear. Yes, there is isolation. Yes, there is panic buying. Yes, there is sickness. Yes, there is even death. But they say that in Wuhan, after so many years of noise, you can hear the birds again. They say that after just a few weeks of quiet, the sky is no longer thick with fumes, but blue and grey and clear. They say that in the streets of Assisi, people are singing to each other across the empty squares, keeping their windows open so that those who are alone may hear the sounds of family around them. They say that a hotel in the west of Ireland is offering free meals and delivery to the housebound. Today, a young woman I know is busy spreading flyers with her number through the neighborhood so that the elders may have someone to call on. Today, churches, synagogues, mosques and temples are preparing to welcome and shelter the homeless, the sick, the weary. All over the world, people are slowing down and reflecting. All over the world, people are looking at their neighbors in a new way. All over the world, people are waking up to a new reality, to how big we really are, to how little control we really have, to what really matters, to love. So we pray and we remember that yes, there is fear, but there does not have to be hate. Yes, there is isolation, but there does not have to be loneliness. Yes, there is panic buying, but there does not have to be meanness. Yes, there is sickness, but there does not have to be disease of the soul. Yes, there is even death, but there can always be a rebirth of love. Wake to the choices you make as to how to live now. Today, breathe. Listen. Behind the factory noises of your panic, the birds are singing again. The sky is clearing. Spring is coming. And we are always encompassed by love. Open the windows of your soul. And though you may not be able to touch across the empty square, sing.
All right, solid. I think we're basically done with this. So I'm gonna leave. Thank you for watching. Have a great day. Hopefully inverted indexes are gonna be much better now.